Welcome to this series of lectures on practicals on soil spectral inference. This is the fifth and last lecture which will focus on estimating soil properties from spectra. So I will illustrate how to fit regression models between spectra and soil properties with example and an analysis in R. So before that, let me repeat briefly the content of the course. So there are two objectives in this course. The first is to provide an overview of the practical steps needed to derive soil properties from infrared spectra. And the second objective is to give examples and simple implementations in the R programming language. So the course is composed of 5 main sections. Each of the sections covers a very specific step that you need to realize to treat soil spectral data. And this current section is about estimating soil properties from spectra, where I will show you how to select a regression model and fit this model on your spectral data. I will also show you how to evaluate your model using prediction validation statistics. And this will be the last course of this series of short lectures. So the question we are answering in this short lecture is how to estimate soil properties from spectra. And the most common way to do that is to fit a statistical model between the soil property of interest and the spectra. Remember from the first lecture, I explained that this relationship between spectra and soil property is very complex because a soil property, for example, the clay content, is not related to a single wavelength, but to a combination of interacting and overlapping regions in your spectrum. So in addition, the spectral data contains many predictors. For example, in a regular spectrum in the visible and near-infrared range, we have about 2000 wavelengths, which we will use as predictor in the statistical model. So these wavelengths are correlated one to another, and the spectra are also correlated one to another. In this figure here, this is the steps to build a spectral library for soil. So you don't need to read it all, and I will not explain it in details because you can find the description in details in many papers and textbooks. What is important to remember is that fitting a model between soil properties and spectra is one of the last steps in the process of building and using your spectral library. And before these steps, there are many other steps that need to be done. And I tried to describe most of them briefly in the previous lectures. So some of these steps are spectral scanning, first step, and then you have the spectra pre-processing. You must do exploratory spectral analysis, but also you should select the samples for wet chemistry analysis. And when all of this is done, we can proceed with fitting a model. Let me start with the most common model for regression in digital soil spectroscopy. So this model is called partial least squares regression. So in partial least squares, we combine principal component analysis and linear regression. And we already explored in the third lecture principal component analysis. So I invite you to check out this lecture if you want to learn more about this. So the advantage of partial least squares is that it is well equipped to deal with multicollinearity of the predictor variables because it uses principal component analysis to reduce the dimensionality of the spectral data. PE-LSR is also a model that is easy to interpret because it provides the scores and the loadings in the same way as principal component analysis. So generally, it is a model that has been tested over many case studies, many data types, and in most of the cases, it provides robust results. So how does it work? In partial least squares, we simply build a linear model between the latent structure of the spectra and the latent structure of the soil property, for example, the clay content. So this means that we make a principal component analysis on the spectra data matrix, called X in our case, and then we also make a principal component analysis on the soil property, but this time making use of the latent structure of the spectral data. So if you look at the figure on the top right corner of the slide, you can see the matrix of spectra X and the matrix or vector of soil property Y. For X, we decompose the spectra data into two matrices called T and P, and we also have a residual matrix called E. For Y, we do the same. We decompose Y into two matrices called U and Q, and we have the residual matrix called F. But this time we define the matrix U so that the inner relation with the T matrix of the spectra is also used. So this means that we describe the soil property by the matrix T and P from the spectra, but also Q from the soil property, and we minimize the residuals of this relationship. So as I said before, the PLSR model, the partial least squares regression models, are easy to interpret. And we can use, as in principal component analysis, the loading values. And we can link the values of the loadings with the wavelengths of the spectra. An important positive or negative value of the loadings indicates that the associated wavelength is an important predictor. So in this figure that I took as example, you can see three loadings corresponding to a partial least squares model fitted to predict the total carbon of the soil. So each color is a loading, and then we use three loadings for this model. And so you can clearly see that some areas have positive or negative values. For example, the area between the indices 30 and 100 and between also 300 and 400 have positive or negative values. By linking these areas to the visible and near-infrared spectra, we know that these areas are linked to organic matter functional groups and also to clay minerals. And this makes sense because we are predicting the total carbon of the soil. Now I would like to introduce random forest for modeling soil spectra. So random forest is a machine learning model based on decision trees. So many people are familiar from decision trees. So random forest has been a very popular model lately, and indeed it can efficiently handle a large number of predictors as we have in digital soil spectroscopy. So random forest is based on bagging, which stands for bootstrap and aggregating. So we build a single decision tree from a bootstrap sample of the original data, and then we introduce a random perturbation when splitting the tree. And we repeat this for all trees that we wish to build, for example, 500 trees. So we have to decide on three parameters when we fit a random forest model. The first parameter is, of course, the number of trees. The second is the minimum node size. And so this parameter is to decide when we decide to stop the splitting of the tree because there is not sufficient data to split more. And finally, the last parameter is called M-try. M-try is the number of explanatory variables, the spectra, that we will randomly subsample at each splitting of the tree. You can see in this figure on the top right corner of the slide that we build several trees. Each tree makes a prediction, and the final prediction by random forest is taken as a combination of all these trees. It's taken as the average of all trees' prediction. And an important feature of random forest is that we also have access to a tool to obtain the variable importance of the model. So in this figure here, you have what is commonly reported in spectroscopic studies, an overall variable importance value for each of the wavelengths. So the two figures show the variable importance using two different statistical indices to measure the importance. So there are many possible indices to measure the importance, but they are all estimated more or less the same way using a permutation algorithm in this case. But all of them might return different or at least slightly different results because they are sensitive as well to the correlation among predictor variables. In any case, we see here that the wavelengths around 1400 nanometers are generally the most important in both figures. So all this relates to the model fitting and better understanding of the model The last slides I show you are about model fitting, are about how to interpret the models. But before predicting, we should ensure that the model can actually predict with sufficient accuracy. And to do this, we need to do a validation of the model prediction. So generally, we agree that a model should not be evaluated on the data with which it was fitted. We call it an internal validation. And this can be useful. An internal validation can be useful for very specific case, for example, to give an indication, but it does not constitute a formal validation of the model predictions. And to formally validate the models, we have two main techniques generally that we can use to evaluate the model predictions. So one of such techniques is called data splitting. So we have the whole data set in data splitting, and we split it into two separate data sets. One part will be used for model fitting, and another part will be used for model prediction and validation. And so generally we take 80% of the data for calibration and 20% of the data for validation, or 75-25%. And so when we predict the data from a validation set, we obtain two vectors, prediction and observation, and we can use them to compute validation statistics or a scatter plot like the one that you can see here. Another strategy to evaluate model prediction is to use cross-validation. So generally, cross-validation is better than data splitting because we use all the data for validation, but this is also slower than data splitting because we have to repeat the process many times. So in cross-validation, we split the data into folds, for example, 10 folds in 10-fold cross-validation. Then we use 9 of these folds for calibrating a model, for fitting a model, for predicting a solve property. And then we predict at the remaining single fold that was not used for calibration. And then we repeat it 10 times. And each time we use a single fold for validation. So at the end, every fold has been used only once for validation. And as before, we can then plot the values of the prediction against the values of the observation in a scatter plot. This is what you see here in this figure. And we can also calculate validation statistics that assess the overall model prediction quality. So we need validation statistics that tell us, on average, how good the model prediction is. And there are many validation statistics that we could use. And each of these statistics represent a specific aspect of the prediction. So usually we report a set of about 4 validation statistics that represent different aspects of the model prediction. For example, we report an estimate of the bias, an estimate of the overall magnitude of the error, and an estimate of the correlation between predicted and observed values. And finally, we can also report an estimate of the amount of variance explained by the model. Let us briefly discuss these validation statistics. So the bias can be shown by the mean error. So the mean error shows the systematic over or under prediction of the values, and it is simply calculated by taking the average of the observation minus the predictions. So ideally, we would like a value close to 0, which means that there is no bias, but the mean error can also be negative or positive if there is a systematic over or under prediction of your data. Another statistic that is very common is the root mean square error. So the root mean square error shows the magnitude of the error, and it is in the unit of the solve property. And ideally, the root mean square error is as small as possible. Then there is the linear correlation. So the linear correlation can be calculated by the square of the Pearson's R correlation coefficient. So the linear correlation square only tells us about the linear association between observed and predicted values. A value of 0 means no linear correlation, and a value of 1 means perfect linear correlation. So finally, we have the coefficient of determination. So there are several equations existing for the coefficient of determination, and this is sometimes confused with the square correlation coefficient. So personally, I call often this coefficient of determination a model efficiency coefficient. So you have the question here. The optimal value for the R square is 1, and the R square can be negative as well. So in this case, it means that the mean of the observation is a better predictor than the model. So in other words, the model is not very useful. So now that we have seen two example models for fitting a regression, and that we know how we can evaluate the model predictions using data splitting, cross-validation, and validation statistics, I propose to have a simple example in R. Here we use again the data from the Prospect R package. So the instructions for this dataset are already given in the second lecture about spectra preprocessing. So you have to load the package using the library function, and then you can load the data using the function called data. And the dataset is called NIR-soil. So for the example using this data, we will do a simple data splitting of the dataset. Even if in most cases, I would rather recommend to make a cross-validation instead. So we start by the function called setSeed with a number inside, just to ensure that when we run again the process after, we always obtain the same results. Then we use the sample function in R and take 75% of the data for calibration, the remaining for validation. And we create two sub-data sets called .c for calibration and .v for validation. So just to illustrate here, you have the total carbon data of the calibration and validation data plotted as histogram. And to plot the histogram, you use a function called hist. What we see using these histograms here is that both calibration and validation data have a similar distribution. And so now we would like to proceed by fitting a partial least squares model. For this, we use the package PLS, which you need to install using the install packages function, and you need also to load. We start by saying that we would like a maximum of 10 components. Then we can create a partial least square model using the PLSR function. In this function, we have to specify several arguments in R. So first, the formula, we make a regression of the total carbon against the spectra. Then the data we use for the calibration dataset are called .c. These are the data that we split before, 80% of the original data. We specify the methods that we use for PLSR. So I invite you to look at the documentation of PLSR for more information on the specific methods. Then we specify the number maximum of components. And here we will let the algorithm shows us what could be a good number of components. And for this, there is a sort of built-in function that makes an internal cross-validation. And so we can plot the number of components against the error. This is what is the built-in function of the PLSR package. And so we obtain this plot, and this plot is similar to what we can get with principal component analysis. It actually tells us that we can use only 4 components to describe our spectral data. So we can use more components if we wish, but it will not decrease much more than the prediction error. So here we decide to use an optimal number of 4 components. So if now we use 4 components and actually show the scatter plot of predicted versus observed, we can see that indeed it is sufficient with 4 components. An important note here is that this is not an external validation, but internal, and we should not use this result to evaluate the final model. It is only here to help us decide on the model parameters. So the fitted model using 4 components can be interpreted. It is the same as for principal component analysis that we showed before. So this is the loadings figure. assume that now you are familiar with the loadings of principal component analysis and partial least squares regression, and that you know how to interpret them. So it is implemented simply with the plot function and by specifying the fitted Peiresian model and the argument loadings, because we want to see the loadings. Then we can evaluate the model prediction using the data for validation that we left aside earlier. And we can simply predict using the predict function in R. So here we have to specify in an argument the new data on which we would like to predict. And we predict into a new object which are called a soil VPLS pred for soil validation partially square prediction. So we plot in a scatter plot the predicted versus observed data from the validation dataset. And I add to this scatter plot the one-to-one line. So ideally, we expect all the points to be close to this line. So finally, I compute the mean error for the bias and the root mean square error to give indications on the magnitude of the error. So the mean error here is close to 0, which is good and indicates no systematic over or under prediction of the total carbon. The root mean square error indicates that there is an average error of 1.1 in the unit of the total carbon. So the unit here is in carbon in gram for 100 grams of dry soil. So this was the 5th lecture. It was about estimating soil properties from spectra. And this is the end of this series of lectures with short applications in the R programming language.